Hello all, welcome to the third lecture of power system stability. In this lecture, we will see the types of stability, then synchronizing torque, damping torque, synchronizing power, damping power, then swing equation. These are the topics which will be discussed in this particular lecture. So in types of stability, we have steady state stability, then dynamic stability, then transient stability. Dynamic stability is also known as small signal stability. Now let's see what are these types of stability. Steady state stability analysis studies the response of synchronous machine to gradually increasing load. It also determines the upper limits of machine loading before losing synchronism. That is what is steady state stability. We mostly deal with slow changes with respect to load, demand or generation or any other slow disturbances. That is what we are going to discuss in steady state stability. Now coming to dynamic or small signal stability, it studies about the response to small disturbances producing oscillations, or we can say a system to be dynamically stable if oscillations do not build up to exceed certain amplitude, or rather it dies out quickly. Then only we'll say that the system is dynamically stable. Now coming to transient stability, it's basically about the response to large disturbances, a large change in rotor speed or power angle or power transfers. It is usually evident within a few seconds. Now to study the stability analysis, we need to know the inertia constant, the concept of inertia constant, angular momentum, and what is swing equation. They play an important role in determining the transient stability of the synchronous machine. So to know the transient stability, to study on the transient stability, we need inertia constant, then angular momentum, and swing equation. So let's see what are these things. Now, what is meant by inertia constant or per unit inertia constant? Inertia constant. It is denoted as H and the unit is megajoules per MVA. It is the kinetic energy stored in the rotating parts of the machine at synchronous speed per MVA rating of the machine. Once again, I'll repeat. It is the kinetic energy stored in the rotating parts of the machine at synchronous speed per MVA rating of the machine. So let's see what is rotor kinetic energy. This is equal to half into J into omega S mechanical. This S denotes synchronous. Okay, omega S mechanical squared. So this is equivalent to half mv squared, right? In linear motion, this is equivalent to half mv squared. as this is a rotational motion, we take rotational speed and moment of inertia of the rotor. So J is basically the moment of inertia of the rotor. Okay, so its unit is kilogram meter squared. Now, what about omega s? Omega s is mechanical radians per second. Okay, now this can be, we can give this as equation 1. Okay. Now omega s electrical. How to convert omega s mechanical to omega s electrical? It is by using the number of poles. So if the number of poles is P, then P by 2 into omega s mechanical will give you the omega s electrical, where P is the number of poles. Okay, of the machine. Now this is equation number 2. Now from equations 1 and 2, we can substitute this omega s mechanical in terms of omega s electrical in equation 1. So we'll get kinetic energy as kinetic energy equals half into J into 2 by P the whole squared into omega s electrical into 10 raised to minus 6 into omega s electrical. Okay, so now this is this part is the M. This is M, which is the moment of inertia in megajoules second per electrical radian. This is M in terms of, megajoules second per electrical radian. So let it be equation 4. Now we shall define inertia constant H such that, what is inertia constant H? To define inertia constant H, we have GH equals kinetic energy. Which is equal to half into M omega s electrical. Right, half M omega s electrical. So kinetic energy in megajoules. This is equation number 5. Okay. Now here G is 3-phase MVA rating. Of the machine. So normally this 3-phase MVA rating is taken as the base. If you are going to find the per unit value, then this will be the rating, will be the base. Okay. So now let's see how some unit conversions work. Watt equals joules per second, right? That means joules equals watt second. What about megajoules? Megajoules equals megawatt second, right? Megawatt seconds. Then what about megajoules per MVA? Megajoules per MVA equals megawatt seconds per MVA, right? Now megawatt per MVA is a, what about megawatt per MVA? Megawatt per MVA is a dimensionless quantity, right? Megawatt per MVA is a dimensionless quantity. Therefore, H can be defined as, now H we will define, H can be defined as inertia constant in megajoules per MVA or megawatt seconds per MVA or seconds, just seconds. Okay, so now from 5, where is your equation 5? Here is your equation 5. Okay, from 5 we are going to get m. M equals to define h, m equals 2gh divided by omega s electrical. Omega s electrical, which is equal to 2gh divided by 2 pi f, right? 2 pi f. Now, how will you get m from here? M equals gh by pi f, gh by pi f. So now moment of inertia in terms of electrical frequency. We have represented moment of inertia in terms of electrical frequency, and now the unit is megajoules second per electrical radian. Electrical radian. This can be equation 6. Okay. Now assuming G as the base, if G is the base, you can convert this into per unit. This in the sense the moment of inertia is now actual moment of inertia. We can convert it into moment of inertia per unit by dividing this with the base. Okay, so if we are assuming G as the base, then the inertia constant can be written as m divided by G base equals hg divided by pi f G base, right? Pi f G base, right? On both sides we have divided with G base. Now we get m per unit. What is m per unit? It is h by pi f, right? M per unit is h by pi f. M per unit is equal to h by pi f. H by pi f, and the unit is second squared divided by electrical radian. Electrical radian. This can be represented as equation 7 or 8. Maybe this can be 7 and this can be 8. Okay. Now, otherwise, alternately, we can write m per unit as h by 180 into f. Then radians will become degree, right? So second squared divided by electrical degree, right? Electrical degree. This can be equation 9. Now, we know that at steady state, torque into omega. What is torque into omega? Force into velocity in linear motion, torque into omega in rotational motion. Power, right? This is power, right? This is power. So if electrical torque into synchronous speed, if you take, this is what? This is electrical power is equal to mechanical power in steady state, right? Which is equal to PM, which is equal to PE, mechanical power and electrical power. That means PM minus PE is, you know that it's the accelerating power. Accelerating power is 0 at steady state, so which is equal to PA, which is equal to 0, right? Now, if PM greater than PE, if PM is greater than PE, what happens? Accelerating power comes into play. At steady state it was 0, now it comes into play. So here in this case, PA equals m d square theta E by dt squared plus d theta E by dt.